And again, in practice, page level locking is a very nice idea because you don't have to lock as many things. Table lock and level locking is a good idea. In practice, systems do record level locking and they may escalate to a higher granularity, but it's unusual for applications to ask for table level locks or database level locks because it does prevent other people from operating. It does happen sometimes, it's just rare. Question?
What is usually the reason for upgrading the granularity? Is there like a specific thing that
you see something where I'm updating so much inside this table, so many different tuples, that it would be easier for me to go ahead and grab the table level lock, because otherwise I'm going to have to keep grabbing tuple after tuple after tuple. And so grabbing a higher granularity lock just ends up being something where it ends up being more efficient and more likely that the transaction is going to be able to complete, rather than going ahead and grabbing tuples and maybe having to roll back because somebody else has updated things, depending on what isolation you're going after. Okay, so, yes?
So if you're doing like a bulk insert or something, it will grab a table level lock?
If you're doing a bulk insert, it might be something where it tries to grab a table level lock. It also might be something where transactions are operating with snapshot isolation or below, and so there's no need to actually have to grab the table level lock because everybody's reading only the tuples that existed when the thing started. So you're not going to interfere with the other things that end up existing. So, I mean, basically this is, bulk inserts get treated in all sorts of interesting special ways. We're going to be coming to logging, but sometimes bulk inserts, you don't even bother logging them, and I'll talk about the implications of that when we get more to recovery. Utilities deserve a lot more attention than they get in the course. They get ignored. I'll give you examples of utilities: backing up the database, recovering a database after a failure, bulk insert, and I'll give you another amusing one. Creating an index is a kind of utility. And upgrading your software to a new version is another interesting utility. And just a very fast comment on that, because it's something people don't usually remember. Upgrading, let's say you want to have a new schema. Upgrading to a new, more complex schema is a hard thing to do right. Upgrading is much easier than downgrading. Suppose that you do the installation and you bring up something you discover that it's buggy, and you want to go back to the old version of the software because your new version had some problems in it, performance problems, correctness problems, whatever it is. Downgrading isn't there, even when you do it very carefully. And very carefully means setting it up so that downgrade is possible, that you don't put in values that the old version won't be able to understand. That's a long, very different kind of conversation, and the whole notion of how you play with DevOps is, again, not a big subject in this course. There isn't a course that fully deals with that. It deserves to be discussed. Optimistic, which do you pick, optimistic versus pessimistic? Mostly the world uses mostly the world uses pessimistic, but there are advantages to optimistic because you don't have to bother gathering locks as you go. The penalty that you pay is like the Russian aviators on A Night at the Opera. You may have to fly back when you're almost there because it turns out that things change underneath you and it doesn't work. And again, optimistic with snapshot isolation is less likely to have to fly back, and like the Marx Brothers Russian aviators have to do, because there are fewer conflicts if you're operating with snapshot isolation rather than serializability. So most real databases actually do use pessimistic instead. So there are a whole bunch of different isolation levels. Snapshot isolation is moderately common, even though it wasn't in '92. But again, read committed is probably even more common, and it is, for example, the default in PostgreSQL and I believe in Oracle. IBM DB2 had serializability as the default for a long time. It doesn't anymore. Okay, so MVCC again is a great thing that for doing snapshot isolation. It means that read-only transactions never have to get restarted. Why? If you're operating with that, because the read-only transaction can read the data that existed when it started if it operates with snapshot isolation, so that all works very nicely. You can just read the consistent version of when you started, but you do have to deal with the version maintenance and the garbage collection. And now, and rather than switch over to another report, But by the way, are Kenji and Kieran here? Kenji and Kieran, are you here? Can you identify? Kenji, Kieran? Kenji and Kieran. Either of you here? Kenji Mak, Kieran Guro? Either not here or not willing to identify themselves. Okay, because I'm trying to do a little bit of team management. Well, we'll figure out another way of dealing with that. I'll try again later. Okay, so now we're gonna start on this. So, first of all, Monday's a holiday, Memorial Day. So, again, remembering the dead wars. Don't be in class because I won't be and the rest of the class won't be, so remember not to show up on Monday. Also, although it's not on the slide, as of Sunday, these evaluation things are starting, the new form of evaluations. I'll put it on the slide in the future, but it's going to exist starting on Sunday and going on until Sunday right before finals week. So that's all there for you to deal with. The Project 3 solution has been posted. You can use our Project 3 solution when you do Project 4. There actually may be something in that we edit, but I'll let you know if we do that. So it's due, the last project, it's due on June 6th, and you'll get a lot of help on that. And the lab sections, including today, there are lab sections Tuesday and Friday. Fortunately, the lab sections don't get locked out on Monday. What is Project 4? Project 4 brings everything together that you've done so far. So the stuff you did in Project 3 with an index, it didn't get tied up together with the relation manager and the RBFM and all the rest of it. Just to briefly tell you about Project 4, here's the idea. You are going to execute a query. You are not going to be executing a SQL query. What you're going to be doing is you're going to have a whole bunch of tests that you can work with that execute queries where you can do things like, let's see, a single relation query, find all the things where this attribute equals this value, find all the things where this attribute is less than or equal to that value. And you're going to tie in your ability to be able to do things with a table scan where you're testing for an attribute value, which we had before, but you didn't really use that much. And also the ability to do the same thing with an index. So there'll be tests that use an index scan and look for equal value, less than or equal to value, stuff like that. But wait, there's more. You also will be dealing with joins. Again, you're not writing a SQL query. You are given a plan. So you'll have things where you have a left table, which you can think of as the outer table. And you'll be looking up tuples, maybe all the tuples, maybe via table scan or via an index scan. You get the things in the left table. And then there will be a predicate that associates the left table with the right table, AKA the inner table. What's the predicate going to be? A simple equal join. This attribute of the left table equals this attribute of the right table. Okay. And you'll be doing index nested loop join, which you know all about. It was even on the midterm. So what happens? You get tuple by tuple, you get the tuples in the outer, AKA left table. And now once you have a tuple in your hand, you'll be getting the matching tuple using an index inside the right table, the inner table. So if I have something r.a equals s.b, where r is the left table and s is the right table. Once I have r.a, I can look up using that value, I can find the tuples that have matching s.b because I've got an index, and you always will have an index on column B of table S, column B of the right table / inner table. So one more time, you'll have to do single table things where you look for things like equal and less than, either using an index scan or a table scan. And then you'll have to deal with joins, but you're given the script that does the join. You just have to implement the functionality that allows you to be able to do the lookup. And oh, by the way, there'll be wrappers that you get given for doing things in this QE, which is query evaluation component. But one of the interesting things to deal with, you didn't have an index catalog in Project 3. Congratulations. You had a table catalog, you had an attribute catalog. Now you get to have an index catalog. What do you put in the index catalog? The assignment tells you. You are going to basically be putting in the information about the index, including the table that it's on, and the attribute that it's on. Your indexes are on single attributes. And also the name of the file that has the index. And so you just end up, and the assignment gives you a whole bunch of stuff for the wrappers for doing this. You're going to be executing things, and you'll have the methods that allow you to be able to do the execution. So in some ways, the fourth assignment may in some ways be the easiest of the four, assuming that you understand what's going on underneath. You're given a lot of wrappers, you know how to create catalogs, you know how to, well, basically, you'll see it, you'll have questions will be answered on Piazza and online, and again, you can use our solution on 3, you can use your own. There is a final exam, as you know, it feels like we were just talking about the midterm because we were just talking about the midterm. A 10-week quarter is ridiculous, but that's what we got, especially given all the material there is in this particular course. Wednesday, June 12th from 4 to 7 p.m. in this classroom, covering the entire term. You don't have to bring Scantron sheets. There will not be multiple choice part. There may be some more true-false questions, other things on it, but you'll be answering the exam on the exam, and there'll be material that corresponds to the projects on it. I don't ask you to write C or C++ on the exam, okay? But you will have things that relate to what's inside the projects that's there. You get to bring in the cheat sheet. I am going to, today, I will post last year's 181 final. You can look at, there isn't an answer sheet for it. If you want to ask me about answers, I will post descriptions of it, but I tend not to post answers to the 181 finals. I do to the 180, but I don't for 181. And again, you'll ask me, you know, how many questions are there? Somebody asked me, I think that on the midterm. I don't answer questions like that because it's useless. Questions can have multiple parts. Some will be easy, some will be hard, some will be true, false, some will be long answers. Basically, it's going to get posted, and you know, it'll give you an idea of what the final is like. And I don't try to answer, the microscopic questions about the funnel because that becomes endless and it doesn't help you that much anymore. So, acid properties: atomicity, consistency, isolation, and durability. Remember what all those things are. Atomicity, everything, all the actions in the transaction happen, all the database actions or none of them. Consistency, if you're going with serializability, you're maintaining your consistency. Isolation, execution of transactions is isolated to the level that the isolation level requires from the stuff that other transactions are doing. And durability, if you do something, it lasts. Other transactions can change it, but even if there are failures, your changes persist. We've already talked about isolation. That is what concurrency control was about. And isolation helps lead you to consistency. But now we're going to be talking about the recovery manager of the database system, and that's where you get the A and the D part. That's what this lecture is about. We've already talked a little bit about it, but now we're going to dive in. That's what lecture 15, which was posted as of earlier this week, is about. So again, atomicity, it's possible that transactions commit. You want to make sure that all the changes actually make it out there, even if there's a failure. It's possible that transactions roll back. And you want to make sure if they roll back, you want to make sure none of their changes are out there. And how do you do that efficiently? Now, there's also the durability. Stuff happens, bad things happen, things crash. You might not have written out all of your pages to durable storage. Or you might have written out changes that aren't supposed to be there. So how do you make sure that everything really does end up happening? So here you have a situation in which you have 5 transactions that are running, and then there's a crash, and maybe T1, T2, and T3 committed, and the commits really happened. But T4 is running, and T5 is running, and then there's a crash, and whatever effects T4 and T5 had, they shouldn't be visible. They shouldn't be there when the system restarts. So anything that rolled back should be rolled back. Anything that was active at the time of the crash goes away. How do you do that? How do you do that efficiently? So we'll assume that we're operating with strict 2PL, which means that we get serializability, and it also means that We don't have cascading rollbacks. Even if you don't have serializability, the same things that we're talking about apply. So again, if you're operating with an isolation level other than serializability and you're playing with, things where you're dealing with, for example, write blocks but not rewrite and read blocks, you still can do everything that we're dealing with. We'll assume for the discussion here that instead of operating with MVCC, that updates end up happening logically in place, that when you do an update, you actually update the data where it was. By the way, why would undo be different if you were operating with multi-version concurrency control? Well, you just go back to the old version. It's undoing is just, you kept the old version around. But you didn't regard the new version as really being there. The new version was tentative. The new version would be there if the transaction committed. So you have the old value and the new value inside the database. With MVCC, you make it so. You make the new version there by saying this new version is the real version now. Talking about how you do that would be a separate lecture in itself. It's actually quite interesting and kind of easy conceptually. I'll give you one sentence on that. You mark new versions with the transaction that they're associated with. That transaction has a state. The state might be active, it might be committed, it might be rolled back. You know what you do, and there's details about the implementation I won't go to. You know what you do to commit a transaction? You mark the transaction as committed. Therefore, when you want to look up and see whether or not the updates that are associated with that transaction really happened, you see that the transaction was committed. There's more detail about implementing that efficiently that goes beyond what I've just said. But it's just a general idea. If you want to make sure that commit is something that's going to end up being atomic, there are a lot of details on that. But we're not going to be talking about MVCC. We're going to be talking about what happens when you do in-place updates, and we'll talk about how you get atomicity and how you get durability. And there are two terms that are very important. And the 2x2 diagram, which isn't a Gartner diagram, Gartner talks about, vision and leadership and technology, and here we're talking about force and steel, and where we want to be in this diagram. And let's talk about what the terms mean. The easiest way of making sure that everything gets committed and everything makes it to disk is every time you have a write, you write it to disk, you force it to disk. And then all the changes that you want are there. You may have to undo some of them if the transaction rolls back, but you can just write everything that you want, and that gives you durability. Nothing gets lost. You still have to handle the undo. But if you're forcing every time there's a write, performance stinks, and the idea is to get performance. Forcing takes time. Waiting until a force completes, even if you're doing other work in parallel, that makes the response time of the transaction stink. Question?
Just in response to the whole response time, do you think that would be a time where the computers are so fast that response time it's easier to do seriability rather than do all this fun stuff with?
So there are a couple of points there. First of all, the serializability versus snapshot isolation is an issue about whether or not transactions end up being delayed by other transactions, either because of locks or because of having to roll back. So that's not a fast computer issue, that's a conflicting transaction issue that exists. So I don't think that you're ever going to have a time where everybody wants to do serializability. On the other hand, and this is something that I haven't added to the code yet, but I will add before next lecture, with non-volatile memory especially, there are other approaches that are different than this. There's a very nice paper, very nice presentations that were done by Joy Alvaraj, who was a PhD student at CMU working with Andy Pavlo, so they wrote the paper together. And it takes advantage, I don't think it's implemented in any real systems yet, but I think it will be a variation of it, something which is called write behind log. And in the context in which you have non-volatile memory, the way that you do all this stuff ends up changing in very, very interesting ways. And again, same deal, I will add it to the coda, and if somebody wants to talk to me about it, I will be happy to go through the paper in detail with them privately. I'm not gonna be going through it inside the class. What I'm emphasizing is that new technologies, new algorithms, new requirements of applications end up changing what's done all the time. We're talking about database, and in some ways slightly old style database, but these issues still exist in different ways with SSD, but they will change with non-volatile memory. Because non-volatile memory is memory that's non-volatile, which means that writing to memory, you get the durability because it's non-volatile memory. So there are interesting things to play with in that context. So again, force, you write everything out, cool, everything's out there. No problem with durability. These may have to undo, but no problem with durability. Just a problem with response time. What about steal? There's stuff that you have inside your buffer frames, which corresponds to changes by transactions that haven't committed yet. And as we discussed already briefly, you could have a page in your buffer frame which has stuff that's been done by a transaction that committed and stuff that's been done by a transaction that hasn't committed yet, okay? And so you have stuff in your buffer frame that corresponds to uncommitted transactions. And if you never write out data for an uncommitted transaction, then that poor committed transaction has to, its data has to hang around for a long time. That's a really bad thing to have to do. Because you'll never, as long as there's an uncommitted thing around in that page, you can't write that page. So sometimes you have to steal either because you run out of buffer frames or because there's a committed transaction, you want to write its stuff out. So if you steal, then you've written out uncommitted stuff. So there's force and there's steal. And the thing is that if you do force and you don't steal, that's trivial, it's just that it stinks. It's really easy to do. The one that you'd like to be able to do is something where you have no force. What does that mean? You don't have to force. Yeah, you'll be forcing periodic. Of course you'll be writing persistently. But you don't have to force every time that there's any kind of write that you do. So you want no force, meaning you write when you want to and need to for performance, but you don't have to force everything that you're doing. And you want steal because uncommitted stuff does have to sometimes make it out because you're writing out your pages with committed data on it. And so sometimes you'll be writing out things that have uncommitted data on them too. So how can you ensure atomicity if you're operating with steal? So you want the no force. No force doesn't mean that you never force, it means you don't have to force everyone. Okay? So a little bit more about steal and force. Okay? And this again is talking about why atomicity is hard, right? So basically you have a current page in a frame and you end up writing it to disk, and there's a transaction which is active which holds a lock on some data inside the page. We're not doing page level locking, we're locking a tuple that's on the page. But that transaction could roll back. And basically, you have to remember the old values so that you can undo. If there's going to be a steal, you have to be an honest thief. You have to enforce atomicity. If steal happens, and it's going to have to happen, you need to be able to undo what's on there. That particular write, again, only for the transactions that roll back. We want no force, okay? But if you don't force all the time, then there could be changes that you made, but the modifications on that page have not been written to disk. So here, even though the force isn't with you, you're not forcing everything that makes it out. Old Jedi man trick. You're not writing everything out that's written. You need to make sure that the changes on behalf of a committed transaction do make it out to disk. If I have a transaction that wrote changes to 100 different pages to commit the transaction, I don't want to have to write 100 different pages. That can take a while. I don't have to write 100 different pages. It takes time. So, steel, I have a problem with undo. No force, I have a problem. I'm gonna have to redo all the changes associated with the transaction, even though I didn't write the pages out. So force and steel, and in particular no force and steel, have a very interesting interaction with each other. So somehow or other, we're gonna have to keep track of the information that allows us to undo transactions that rolled back and to redo transactions that actually committed the work that's in them. And by the way, I will emphasize, I want this stuff to be idempotent. Idempotent means doing the same thing twice, gives you the same result as doing it once. Why do I want that? Well, some things made it out and some things didn't. And so if I end up applying the change again, I don't want to, if I added $10 and changed somebody's salary from 100 to 110, I don't want to make the salary 120 by doing the transaction again and changing it. I want the thing to be 110. I want to get the actual same result. So the basic idea of this is something called a log, which I've already briefly told you about. And the log has records for every transaction, interspersed with every other transaction. And what you do is you have the redo and undo information. You have records that have the redo and undo information for every transaction. The redo is going to be necessary if you have an insert or an update describing what work would have to be redone. If you have the committed transaction, you haven't forced out the changes to it, to persistent storage. The undo is necessary if you have a update or a delete, because the update could have changed things, and you have to go back if the transaction ends up rolling back. The idea is that there is a file which you keep appending to, and you do not put it on the same storage device as your database. You know why? If that device fails, you want failure modes of your log and your database. And your database may be on many different disks, and I'm not going to go into it, but often logs may be on multiple disks as well. You don't want to let a failure of one medium, kill parts of both the log and the database. So again, you end up writing the changes to the log. In particular, if I have an insert, I have to write the entire record that's inserted. If I have an update, I only have to write the fields that were updated, the old and the new values. I don't have to write the whole thing. If I have something that's 1,200 attributes in it, I only have to, and I update 2 of them, I only have to write the old and new values of the 2 that changed. Because the rest of it, it's all the same. So I only have to write the description of the changes. So the log is an ordered sequential list of redo and undo actions together with some other records that we talk about. And the log record contains the following things. The transaction that made the change, gives you the transaction ID. Every transaction has a transaction ID, strictly increasing. You're playing with, yes, you can wrap around, but with 64 bits, that's a whole lot of transactions. With 128 bits, it's even more. The ID of the page that we're talking about, the offset and the length, something should remind you a whole lot of an RID. You basically have the information about the changes that you're making. There are other RID specific variations of this that get played with. Okay, but you end up having basically the description of the old data and of the new data, and additional information that we're going to come to. So now we're going to come to write-ahead log, aka WAL. And there's the 2 really important things that are going on with write-ahead log and why it's called write-ahead log. It's called write-ahead log because there are things that you have to write to the log ahead of some other things. Good name. Remember that write-ahead log is law spelled backwards. An example of a joke I haven't made before, and from the laugh it got, I'll probably never make it. So here is the law about write-ahead logging. Basically, as the name suggests, you have to write the log record that describes a change, update, including insert and delete, you have to write the log record that describes the change before the corresponding data page that has that change gets written to disk. The log record for each change has to be written to disk before the page that has that change gets written to disk. Write ahead log. Why do you need to do that? Once you've written the data page to disk that has the change, how do you undo it? Well, the way that you'll be able to undo it is because the log record has the information that allows you to undo it. But if you don't write the log record before you write the change, you're out of luck. If you write the log record before you write the page, then you'll be able to undo it because you'll be able to undo using the log record if the transaction rolls back. But if you neglect to write the log record before you write the page, you're out of luck on the undo because you don't know what you should do to undo what you did. You need to write the log record so you can actually do the undo. Try saying that 3 times fast. That's why it's write ahead log. And moreover, before you commit a transaction, you have to make sure all the log records for that transaction are out there on disk. Why do you need number 2? If the transaction is going to be committed, you are committed to redoing the transaction to make it durable, even if there's a crash. So before you write the commit record and say the transaction is committed, all the log records associated with the transaction have to be out there on durable storage, e.g. disk or SSD. Because without that, how do you redo? If we're done, we're best done with a log record that allows you to redo. If you don't have all the log records on the transaction out there, and there are some pages that were supposed to have changes made by this transaction, how do you redo them if there's a crash? But if you have all the log records, which means all the undo and redo, if you have all the log records for the transaction out there on disk, on durable storage, before the transaction commits, then if there's a failure, and you say, oh, this transaction committed, I better make sure all its changes happened. Every log record describing what the transaction was supposed to be doing can be redone. And because it's idempotent, when it's redone, it gives you the same effect, whether it already had been forced out or not. So both of these are write ahead. You write the log records for a transaction before you write the pages that have the change that log record describes. And before you can do the commit, you write all the log records of the transaction. The first one allows you to undo if the transaction rolls back. The second allows you to redo if the transaction commits. Question?
So just to clarify, right now logging is on top of snapshot isolation?
Logging is used with all the isolation levels.
Okay.
Logging is independent of the isolation level. Logging is what allows you to get the atomicity and durability regardless of isolation level. The isolation levels play in with the locking or the pessimistic concurrency control or the optimistic concurrency control or other methods of concurrency control. Here we're talking about atomicity and durability separate from which isolation level you have. Basically, however you're operating, you want to make sure that what the transaction did really happened if the transaction committed, and it didn't happen if the transaction rolled back.
So I think I'm really trying to get at is that for the logging record, it's got this idea of where it's only storing the difference. So is it storing like there's this version of the database from this point that we're basing everything on?
You're getting to something that's very real when we get to checkpoints, but what we're talking about here is basically the only reason you need a difference is that suppose again that you have 1,200 fields in the record and you only updated 2 of them. What does the redo have to redo if there's a change? It only has to redo the change in the 2. The others are still there. Okay, what does it have to undo if it has to roll back and the page with the 2 change fields made it out to disk? It only has to undo the changes to the 2 fields. It doesn't, it has to deal with the delta. It has to do with undoing the changes, because the rest of it's still in the correct form. And it only has to do with redoing the delta, redoing the changes, because everything's okay. It doesn't have to describe everything, it only has to describe what's changed, because the other stuff is still there because it hasn't changed. So the remaining 1,198 attributes are still cool, whether you have to do a redo or an undo. They haven't changed, so they're still there.
So, how long are we really keeping those logs? Are we deleting them immediately after it's no longer of use? Or are we keeping like a certain number, or?
Great question. Can you hold off until I get to checkpoints?
Sure.
And then I will check your point. Okay? All right. And if I don't, let me know. I'm sure you will. And thank you for asking the question. So, number one guarantees atomicity. Number one guarantees that you're going to be able to undo the things that didn't happen. Number two guarantees the things that did happen are durable. So that gets it. And now we're going to talk about an algorithm which is due to C. Mohan at IBM and other people, which is called ARIES, spelled A-R-I-E-S. And we'll see how this works. And there are, again, other interesting variations of it that have been done since then, both different algorithms and using different types of devices. But we're going to talk about the classical ARIES algorithm. And again, people who want to talk to me about other approaches, please let me know. I'm going to add some slides pointing. I already have Coda on this, but I'm going to add some other additional things on it. So basically, what's going on? Every log record has a unique LSN. Please get used to the term LSN. We're going to be putting various prefixes in front of LSN and talking about particular LSNs as we go through this. So get LSN straight. LSNs are increasing numbers that exist in every log record. You're right, log record 42, log record 43, log record 44. LSN is the log sequence number. It keeps going up, okay? And now, this thing tells you about two other kinds of LSNs that are discussed. And again, they refer to the log sequence number. So log sequence number is, again, something, you have this infinite log that you're writing, and yes, you will have to garbage collect and not keep everything around forever, but we'll get to that. But we have these log sequence numbers. Every time you write a log record, you append to the end of the log, and you get an increasing LSN. So one by one, the LSNs go marching along. Transactions are interspersed in the log. You don't have all the LSNs for one transaction and then the LSNs for another transaction. They keep going up. Now there's a particular LSN that you associate with each data page. What LSN do you associate with that data page? The log sequence number of the most recent log record that has an update to that page. Log records are writing to that page. If you have a page in memory, maybe that there were no changes to the page. Okay, you've got a null page LSN, not a big deal, that's fine, nothing. But it could be that I do a write to the page and I generate a log record. I did an update on that page, I generate something with LSN 49. I change another tuple on that page, and that LSN is 52. I don't keep track of both 49 and 52, I just keep track of 52. So I keep track of the latest LSN that changed the data on that page, and that's called the page LSN.